When people think about fighter jets, they remember the supersonic speed, the guided missiles, or the stealth technology. Almost nobody pays attention to the tires. But in the most violent moment of each mission, the carrier landing, they're what receives the direct impact. A fighter can touch the deck at over 240 kilometers per hour and stop completely in less than 100 meters. All that energy needs to be absorbed in 2 seconds. The first point of contact with the surface is the tires. They're not inflated with common air. They're filled with dry nitrogen. The reason isn't military convention, it's risk elimination. The most demanding instant for fighter jet tires happens in a scenario that has no equivalent in commercial aviation. When a jet lands on an aircraft carrier, it's not a gradual touchdown followed by gentle braking. The aircraft hits the deck at approximately 240 to 250 kilometers per hour with the tailhook extended. That hook catches one of 4 arresting cables stretched across the landing area. From that moment, the aircraft goes from full landing speed to complete stop in roughly 2 seconds. The deceleration distance is around 90 to 100 meters. The forces involved are extreme. A pilot experiences between 3 and 4 Gs during the arrested landing. The tires, stationary before contact, must instantly spin up to match deck speed. They absorb vertical impact and forward deceleration forces simultaneously. This isn't a single event per flight. Combat sorties involve multiple takeoffs and landings within hours. A single deployment can subject tires to dozens of these violent cycles in rapid succession. Temperature swings add another layer of stress. At 40,000 feet, the ambient temperature can drop to -50 degrees Celsius. The tires are exposed to that cold for extended periods. Then, within minutes of landing, those same tires sit adjacent to carbon brake assemblies that can exceed 1,000 degrees Celsius. The thermal shock is immediate and repeated. There's no gradual warm-up, period. The weight distribution is also different. An F/A-18 Super Hornet lands at roughly 20 tons, but that weight is concentrated on just 3 tires, 1 nose gear and 2 main gear tires. Compare that to a commercial airliner where hundreds of tons are spread across 12, 18, or more wheels. The force per tire in a fighter is proportionally much higher, and because carrier decks are shorter, there's zero margin for gradual deceleration. Everything happens in an instant. You can see the tire smoke on every carrier landing video. You can observe the visible compression and deformation as the aircraft slams down and catches the wire. The tires are subjected to conditions that would destroy standard automotive or even commercial aviation tires within a single cycle. So here comes the question that matters. With all that weight and speed and heat, why wouldn't they just use regular air to inflate them? That's where the chemistry matters more than the engineering of the tire itself. Air seems like the obvious choice. It's free, it's everywhere, and it's what inflates nearly every tire on the planet. But air isn't a single substance. It's a mixture, roughly 78% nitrogen, 21% oxygen, and traces of other gases plus water vapor. In normal conditions, that mixture works fine. But fighter jet tires don't operate in normal conditions. They operate in extremes, and those 2 components, oxygen and moisture, create specific problems that become unacceptable risks in military aviation. Start with oxygen. Oxygen supports combustion. In the presence of heat and flammable materials, it accelerates burning. Fighter jet brake systems use carbon composite materials specifically because they can withstand extreme temperatures without failing. During an arrested landing or an aborted takeoff, those brakes can reach temperatures well above 1,000 degrees Celsius. The tires are mounted millimeters away from that heat source. If a tire is inflated with oxygen-rich air and develops even a small internal crack or puncture near the brake assembly, the oxygen inside can feed a fire. It's not a theoretical risk. It's a documented failure mode. This isn't just about making things safer. It's about removing a variable that has caused incidents in aviation history. Then, there's moisture. Regular air contains water vapor. The amount varies depending on humidity, but it's always present unless the air has been specifically dried. Water vapor behaves unpredictably under rapid temperature changes. When a tire goes from -50 degrees Celsius at altitude to sitting next to a 1,000-degree brake assembly on the deck, the internal pressure doesn't just rise predictably. The moisture can create localized pressure spikes as it expands and contracts. That unpredictability makes it harder to maintain precise pressure specifications. And in a system where tire pressure directly affects landing performance and structural integrity, unpredictability is a failure point. Moisture also accelerates corrosion. Fighter tires operate in salt-rich environments, especially on carriers where seawater spray is constant. The internal components of the wheel assembly, the valve stems, the bead seats, are made of aluminum alloys and steel. Introduce moisture into that sealed environment, and you create the conditions for galvanic corrosion. Over time, that weakens the structural integrity of the wheel assembly itself. It's not an immediate catastrophic failure, but it's cumulative damage that shortens service life. Nitrogen solves all three problems. It's an inert gas, meaning it doesn't support combustion. Even at extreme temperatures, nitrogen won't feed a fire. It's also dry when properly sourced. Industrial nitrogen used for tire inflation is stripped of moisture content, so there's no water vapor to create pressure unpredictability or internal corrosion. And while nitrogen does expand with heat like any gas, its expansion curve is consistent and predictable because there's no moisture complicating the thermal behavior. The pressure itself is another factor. Fighter jet tires operate at 300 to 350 psi. That's significantly higher than commercial aircraft tires at around 200 pounds per square inch, and vastly higher than automotive tires at 30 to 35 pounds per square inch. That elevated pressure is necessary to support the concentrated weight and maintain tire shape under extreme deformation. But higher pressure also means any internal instability, any unexpected expansion or contraction, has amplified consequences. Nitrogen's predictability under pressure and temperature swings is what makes those high-pressure specifications safe and reliable. It's not just borrowed practice from commercial aviation. It's engineered necessity. Military specifications go further than civilian standards. The tires must meet MIL-PRF requirements, which include testing for battle damage scenarios, contaminated runways, and extreme crosswind landings. Nitrogen inflation is part of that. Certification, because it eliminates variables that air introduces. It's not about convenience. It's about removing failure modes that have measurable consequences in combat operations. But that raises the next question many people ask. What if the nitrogen leaks? What if a tire loses pressure during a mission or suffers combat damage? The concern is valid, but the system is designed with that scenario in mind. Nitrogen molecules are larger than oxygen molecules. That means nitrogen leaks more slowly through small punctures or valve degradation compared to air. If a tire develops a slow leak, the pressure loss is more gradual. Ground crews get more time to detect it during pre-flight checks. In the case of combat damage, a puncture or tear that compromises the tire, nitrogen doesn't worsen the situation. A tire inflated with air that suffers damage near a hot break can introduce oxygen into an already critical thermal environment. Nitrogen remains inert. It won't ignite, won't support combustion, and won't create secondary fire hazards even if the tire is shredded. That's a meaningful difference when an aircraft is trying to land on a carrier deck after taking ground fire or debris impact. Field maintenance is another consideration. Carriers and forward airbases are equipped with nitrogen storage and generation systems. It's not a logistical barrier. Portable nitrogen tanks are standard equipment in aviation maintenance kits. The infrastructure to support nitrogen inflation exists wherever fighter jets operate, from supercarriers to austere forward operating bases. The logistics are solved. Fighter aircraft also have fewer tires than commercial jets, which means less redundancy. An F/A-18 has 3 tires total, 1 on the nose gear and 1 on each main gear strut. If one fails, there's no array of additional tires to distribute the load, like on a Boeing 777 with its 12-wheel main landing gear. The design compensates with stronger individual tires and more robust failure tolerance, but that makes the reliability of each tire even more critical. Nitrogen inflation contributes to that reliability by removing the variables that air introduces. Maintenance cycles reflect the intensity of use. Fighter tires are typically replaced every 100 to 200 landings, compared to 200 to 300 for commercial aircraft. That's not a failure of the tire, it's a reflection of the operational intensity. Each carrier landing subjects the tire to forces equivalent to dozens of commercial touchdowns. The wear rate is simply higher, but part of maintaining that replacement schedule is ensuring consistent tire pressure. Nitrogen makes those pressure checks more reliable because there's no moisture-driven drift over time. Certification standards for military tires go beyond what civilian aviation requires. The testing includes simulated arrested landings at maximum weight, tire performance after exposure to jet fuel and hydraulic fluid, and structural integrity after partial deflation at high speed. Nitrogen inflation is factored into those tests because the tire's behavior under stress is partly determined by what's inside it. The inert, dry properties of nitrogen are part of the performance envelope that gets certified. But the story doesn't end with inflation. Nitrogen is one piece of a larger thermal and operational management system. The carbon brakes, The hydraulic systems, even the oxygen systems for the pilot, all use inert or controlled gases to manage heat, pressure, and chemical stability. Nitrogen in the tires fits into that broader philosophy. It's not an isolated choice. It's part of a design approach that eliminates unnecessary chemical reactivity anywhere it could compromise safety or performance. Mission readiness is the ultimate measure. A fighter jet on a carrier deck is either mission capable or it's not. There's no partial credit. Tire condition and pressure are part of the pre-flight checklist. If a tire doesn't meet specifications, the aircraft doesn't launch. That's a binary decision, and it's based on precise measurements. Nitrogen allows those measurements to be more predictable because the gas inside the tire behaves consistently across the temperature and pressure ranges the aircraft will encounter during the sortie. The cost difference between nitrogen and air is negligible in this context. A single F/A-18 Super Hornet costs over $70 million. The avionics, the weapons systems, the trained pilot all represent enormous investments. The cost of nitrogen to inflate 3 tires is a rounding error. Military procurement doesn't optimize for the cheapest inflation method. It optimizes for the method that best supports mission success and pilot safety. Carriers have onboard nitrogen generation systems. They don't depend on shore-based supply. The ship can produce nitrogen as needed, which means the aircraft can be maintained and reinflated during extended deployments without resupply. That operational independence is critical for carrier strike groups operating in contested or remote waters. Training reinforces the importance of proper tire maintenance. Pilots and deck crews are trained to recognize signs of tire degradation, abnormal wear patterns, and pressure loss. Pre-flight checks include visual inspection and pressure measurement. It's not assumed that the tires are fine because they were fine yesterday. Every flight begins with verification. In the end, fighter jets don't use air to inflate their tires because air introduces oxygen and moisture. Both create unacceptable risks in an environment defined by extreme heat, rapid pressure changes, and zero tolerance for combustion hazards. Nitrogen eliminates those risks. It's inert, it's dry, and it behaves predictably across the operational envelope. It's not a luxury. It's not military tradition without reason. It's a precise engineering solution to a specific set of problems that only exist at the edge of what aircraft and their components are asked to endure. And if you've made it this far, subscribe to the channel, hit the like button, and turn on notifications so you don't miss the next videos.